Reddy garu,
Sir,
how many participants are there from outside Andhra? Any idea? Very crudely.
majority are from outside AP, sir. As per the registered participants.
Yeah. Okay. Dr. Minor Babu. Hello.
Good morning, sir. Good morning, sir. Sir, good morning, sir.
You are from which institution? Just to introduce yourself.
From JNTU Kakinad, sir. From JNTU Kakinad, sir.
When did you join?
From 18th, sir. Oh, okay,
quite
sir.
some time.
In the college 2008, sir. 2008.
I don't know.
2008 December, sir, in civil department, sir.
Okay. Thank you.
Okay, sir. Thank you very much.
Dr. Maheshwari, I think Dr. Avari Maheshwari. Hello. Yeah, Dr. Mahesh Babu.
Good morning, sir.
Good morning. Can you introduce yourself?
Yeah, fine, sir.
You are from which institution? I forgot.
Yeah, I tried, sir. Actually, this technical problem.
No.
It's a
Where
very
from
nice
you?
program, sir. Conducting
Hmm.
well-planned program, sir. It's a very interesting and very nice program, sir.
Which institute you are working now?
Now I am working in VB8, sir, Vigyan Bharati of Institute of Technology in Hyderabad.
Okay. Uh-huh.
Yeah.
Anyway, nice to hear you. Where from you got your PhD?
JNTH Hyderabad, sir.
Achha, okay. You are kind of
Yeah.
good.
And MTech also from JNTH, BE from College of Engineering, Usmania University in 1989.
Hmm. And you are born in Hyderabad?
Yeah, no, the Karimnagar district.
Yeah, okay. Good.
Yeah, my specialization is transportation engineering, sir.
Hmm.
So this is very much interesting. This soil and this properties and that design of like foundations very useful for me.
Yeah,
They,
nice to know that actually because Professor Sachin Reddy has got the total width by inviting
yeah,
various speakers actually. I think the
yeah.
entire subject is being covered in a different way than a normal textbook kind of picture because we are trying to give an overview of the situation actually.
Yeah, excellent program. Evening time, it should be around 5:30 because that is 4 o'clock.
Mm.
We are in college, sir. Actually, uh,
Yeah,
so
but individually it will be difficult. So something you
yeah,
have
yeah.
to
Yes,
discuss now.
now it's comfort, sir. Morning and evening,
Yeah.
not individually, but orally.
Because I think he has tried to see that you don't miss your normal duties normally. So adjustment is
Yeah,
required, and
yeah,
to make a balance is very difficult for any organizer.
yeah.
So,
However, yeah, YouTube link given us, sir.
yeah,
It's
yeah.
very useful for us.
Mm. Sometime back, I got invitation from your college. I think long back for one
Yeah,
lecture on geosynthesis, something like that. I think.
yeah, yeah.
Oblige it. I think maybe you called me. I don't know, but
Yeah,
you can give one
Kalyanram,
lecture
Kalyanram.
on the subject.
Yeah.
Sir,
If
we'll
you're
start.
interested, I can send the link to you because from Monday onwards, evening 8 to 9, I'm giving lectures in IIT Gandhinagar for our students actually.
Okay, sir.
I can
Okay.
pass the link to you. It is a different way in which I'm covering actually. That is,
Definitely, sir.
I bring them up to the latest IS 37, 2018-19 version, and a
Okay.
bit of airports and a bit of this one overall actually. What is the total coverage I'm going to give?
I
Because
see.
I am of course teaching a regular course on geosynthetics at IIT Gandhinagar. That means online only. I've done it earlier also. All of them are of course available in the IIT Gandhinagar website actually, specially created for this called iGrip.
Okay,
You find
okay.
all the lectures which I'm giving and my colleagues are giving also, and it's the latest on the subject basically. Of course, right now I invited Dr. Jimmy Thomas to give the lectures, and then I invited earlier Dr. Anil Dixit. So I always make it like that because the best in the subject I
De-
bring them,
Definitely, sir. Yeah, yeah.
and to reduce my commitment, I mean my number of lectures on the basics of payments actually. I
Okay.
maintain the extra lectures actually. Because
Okay,
the
sir.
students are brought and level to what I'm talking on geosynthetics, basically payments. So I can
Okay.
you can write to me, you can send a mail to me. I will arrange to send a link to you.
Yeah, definitely,
Monday to
sir.
Saturday, I think 6 lectures, 8 to 9, 9 p.m. I mean in the evening.
Okay. Definitely, sir. How to contact you, sir?
No, you
How
contact my email ID. What is there? I think this is known, in the sense that I can tell you right away. You can
Okay, sir.
contact me at gvrao.19.
Pardon, sir. Tell me, sir.
gvrao.19
GV Rao
dot 19 at
dot
gmail.com. Yeah,
19
that's all. At gmail.com.
I hope
19
you
only.
in chat box, right? You
I
can see.
think chat box Professor Reddy has given already.
Okay, sir. I will check, sir. Thank
Sir,
you.
we'll go for this session, sir.
Yeah, I think we are getting
A
delayed.
very
Yeah.
good morning to all of you, and I welcome Professor G. Rao sir for delivering his lecture on the third day of our program. So during the morning session, we'll have a lecture on settlement analysis of footings. So I request Professor G.V. Rao sir to deliver his lecture on settlement analysis of footings in granular soils as well as Kojo soils.
Yeah.
Please. Sir.
Yeah, thank you, Professor Reddy garu. I hope my screen is visible now.
Visible, sir.
Okay, thank you. And of course, audio is okay for everybody.
Okay, sir.
So this is third session I am giving you on the general subject of shallow foundations. And two things we emphasized. One, of course, is that we are giving a kind of overview. We are not covering every aspect in great detail, like in a class, because I think I mentioned this before also. If you take the subject of geotechnical site investigation, it's almost in PG classes, it is almost one semester course or at least half a semester course. And same thing is true with the foundations also. Foundation engineering, usually both deep and shallow foundation is at least one semester course. Now, this whole thing is being condensed in a different way, very nicely by Professor Janan Reddy to see the various aspects actually, both in teaching as well as practice. So, in trying to understand this, yesterday we tried to look at the basic philosophy of Father Oswald Mackenzie in trying to arrive at a format for determining the bearing capacity. And that was based upon his own experience. He derived the equation for what we call continuous footing, you can say, or wall footing or something like that. In that case now, once he got more experience, basically, he revised the equation to suit the different shape of the foundations, both circular and square foundations. He has actually modified that original equation format. And subsequently, of course, we have several researchers and field engineers, and with their own experience, and with more theories coming up now, we had these various series by Scampton and I can say by Vasek, by Meyerhoff, by Brinch Hansen, by Bella, and all of them led to a simplified form, an equation which is not as simple as that, but including various other factors which we normally expect to happen. We had them from the Brinch Hansen theory as a depth factor, inclination factor, and so on and so forth. Okay. And then also these equations considered the effect of the ground, the ground on which these foundations are going to rest, whether it's horizontal or inclined. And also the base of the foundation could be inclined in some cases. So all these variety are considered in great detail. And luckily for us now, the IS code, as the Indian Standard Code, actually adopted these things in the latest way. But I think I also drawn your attention to the fact that in the beginning itself, I shown the first paragraph of the relevant code and bearing capacity determination that there are various series now, and then naturally judgment is also required in trying to pick up a theory or implement it now. Actually, Mr. Ravikaran Nanjala has raised a lot of issues actually, which I'll address towards the end of this session. The point is that as a structural engineers, we have a lot of small issues which are there. So far as they are concerned with the geotechnical aspect of it, we will try to clarify. The rest of it, of course, is structural design. We'll try to look into that also, when time permits now. The point we are trying to make is now that none of theories can actually predict. That means 100% correct any situation actually, because they are all generic equations now. They consider generalized mass basically, barring that on slopes and layered soils. They are obviously taking everything into a classical way of semi-infinite, homogeneous, elastic half space. It's not really so. Soil is never like that actually. And we have seen even the general shear failure theory or punching or local shear, all of them are actually basically depending upon the basic soil characteristics. But one thing we understood very clearly is that for determining the bearing capacity, it is very important for us to find out the strength characteristics, that means angle of intersection, go and intercept very correctly. Because every degree change is going to bring out a disproportionate change in the bearing capacity factors. That is something which you have to remember always. And also, we ought to remember that when we derived it, of course, barring the latest edition of, latest correction factors Hansen has given now, it is important for us to know that if you're not considering these inclination factors, what's going to happen now? If once you got inclined load at moment now, the foundation is going to slide actually. If the foundation is going to slide, that means the basic resistance at the bottom, the friction resistance of the bottom of foundation, the soil may not be enough to take the inclined load now. But other thing which probably I forgot mentioning is that in all these cases now, we are actually taking into consideration that the foundation base of the foundation is actually highly frictional. It's not smooth at all. If it is smooth, even vertical load also, it may start sliding and give you less bearing capacity actually. So this aspect we will also consider in detail in my last lecture, which is going to be given on 30th of this month, wherein we are going to consider foundation improvement by using Newton's links now. I will elaborate this aspect of what is the importance of friction on this. The other point we are going to say is that if that is going to likely to slide now, what are the things which are going to prevent this sliding now? Is what we have to see now. Sometimes we have shear keys in this now. Of course, shear is also meant for some other reason. And then we are also considering at the side of the foundation now, what is earth pressure generated to prevent the sliding? Obviously, when it is pushed on one side, say it is going to push to the left side now, the passive pressure is going to be created. On the other side, obviously, it is active pressure. So it is always PP minus PE, which is going to come into effect now. So this is the function of the thickness of the foundation now. So what I'm saying is that these are not written in code of practice, but then the structural engineers use this appropriately such that overall design is done. Now, if time permits, towards the end of the lecture, I will deal with some of the small issues wherein the actual foundation is being designed. What we are considering at the beginning is determination of bearing capacity based upon, of course, the strength characteristics of the soils on which the foundation is resting now. And today we will focus upon how to determine what are the kind of settlements which could be there, whether immediate or long-term settlements, and how to calculate them, and how to find out how long it is going to take for the settlement to occur. So these are aspects which are considered again independently. Okay, towards the end only, we'll be able to put them together and see how a foundation is really designed, because the foundation has to take care of both the bearing capacity as well as settlement now. It's very easy for us to say that whichever is the least we are going to consider. And that is not the end of the story, because more often than not, we have, of course, many columns, let us say, in a multi-story building, and each column have different loads actually. And how to convert these loads means obviously the column size, the foundation size is going to be different. And if that is going different now, is the settlement going to be same? It can't be. So when once the question of different settlements is going to occur now, the structural capacity of the entire frame of the structure is going to give you differential loads. Now, this is not considered by all people, but obviously it's a matter of concern for structural engineers who design the structural frame actually. And in the same manner, we also require a modulus of velocity of the foundation now. And I skipped that plate load test because plate load test is not really representative of this now. But if you see standard books like Bowles now, will also give you after once you know the corrected SPD value, from there, or N value, from there we can also assess what is the modulus of the foundation. So that is why I didn't want to do that. And that is more representative of this entire soil spectrum, not just beneath the foundation only. So having said that now, so for inclined loads, we have to think carefully. The foundation has to be frictional, obviously. It has to be rough surface now. Sometimes, in order to ensure that the concrete is not lost now, people also place a plastic sheet actually. Plastic sheet means obviously it's not going to give you no friction at all. Okay, so that is something we have to always keep in mind when assessing the overall situation. So coming to the settlement aspect of it, which we are going to conduct now. What do we mean settlement actually? What we really mean is physically is that it is a non-recoverable or plastic settlement when loaded. When the foundation is loaded now, there is going to be a vertically downward movement. And so that is what we are calling as non-recoverable or plastic settlement. And this, of course, occurs essentially more in the long-term basis on saturated soils, and it is going to be time dependent. In an unsaturated soil or in a sandy kind of strata, it is going to be almost immediate or can be considered elastic also. So by that process now, we're already saying just by common sense that when once you start constructing a foundation on any given soil, we are first going to have some immediate settlement. Sometimes we call it as elastic settlement. And then, of course, we are also going to consider the long-term settlement. And by and large, we call this long-term settlement, again, we divide into two portions now. One, which occurs due to the dissipation of excess forward pressure, which we'll discuss more in detail. And then also, then we other part of settlement, which we call a secondary consolidation, actually, which is probably more prominent in very soft clays and organic clays, which we are not really focusing today. So with that kind of thing now, the foundation soil is going to be very important. That means the uniformity of the soil is very important. Now, in a typical case now, in a typical case like what we are seeing on the right-hand side of this picture, so on the right hand of this picture now, we have got a very tall structure, let us say, and the structure, if it is got almost similar kind of column loads, which is not possible, but anyway, let us assume that there is a vertical movement. It's of course a standard scale anyway. There is a vertically downward movement now, which we call settlement now. But this settlement is going to actually cause some cracking in this area also, in the neighborhood area, which could be portico, which could be just open hall, something like that now, which could be entrance to the hotel or something like that now. So this is also going to cause issues now. And that means even if the soil is going to be same kind of soil in the entire structure, still we may have causes for worry, let us say, causes which we have to take care of to minimize the cracking and other distortion. And of course, we have a classic case of the Tower of Pisa, and wherein we know that the soil below actually is not really as uniform as we expect to be. And we understand by a lot of studies, these studies have been going on for decades actually. Some of the best experts in the world have really given up idea on that now. Then they use the solution which you can't even think. I think you read the literature, you'll find out now. But there is obviously a joke on that. I skimmed a little on the foundation, but no one will ever know the difference. Yes, people always know because whatever is happening below the ground is reflected on the structure basically. So that is something happened. Some people also say there is no glory in the foundation because foundation, if it's good, nobody bothers about it. If it's bad, everybody will curse you. But then it is shown up in the structure actually. Whatever is happening in the ground to the foundation structure. And this is also very important part you have to realize now. We got a foundation means actually the foundation structure like our shallow foundation or deep foundation, but also the soil, both together form the foundation. The foundation structure part is part of the structure, it is a substructure you can say, and the soil below. So these two have to act together actually. So we are of course assessing the soil itself basically and its uniformity and directness and things like that now. But then we have to really see what kind of foundation is going to suit to transfer the vertical loads of the structure onto the soil appropriately. That is the job which we are going to bother about it, and not, as I mentioned repeatedly, just fitting some equation values by simple testing in the laboratory or field into the equations. That is meaningless. So again, I am showing you actual the Pisa Tower, of which I just talked now. But what we find is that in the what we call as the Palace of Fine Arts, in fact, in Mexico, if you just see the YouTube now, if you just search for this in the say Google search, actually, you will find so many pictures and so much write up on this now. The point we are trying to say is that this particular structure, Palace of Fine Arts, constructed 100 years back, is still settling. It settled, I think, by few meters actually. The structure, nothing happened. But then we will see what all happened towards the end of this presentation. So point is that we can't have defense settlement, we can't have too much settlement also. So how to control this? How to make the structure as expect to be? Is it something very important? Is aesthetics important? Or the function is going to be important? And the economy is going to be important? All of them will come into picture when we decide this. So this settlement, which we normally say is consolidation, consolidation really means in a saturated low permeability soil, that means obviously clays, under external loading is about building up of the effective vertical stress by dissipating the initial excess forward pressure through the drainage. Now, what exactly this means now? Once you place any load, of course our foundation in present case, on a soft clay, on a clay which is saturated, that means obviously it is it's called water table. Okay, in this kind of thing, the moment you place a load now, the entire load which I'm placing is converted as actually excess forward pressure. Now, there is a way in which this forward pressure is dissipated through permeability of its own, and other case, of course, would create this path for quick flow. But depending upon the kind of soil, depending upon the existence of the, you can say, granular soils at the top or bottom of this clay, which is going to consolidate, what is going to happen now? This excess pore pressure is going to be dissipated. It may take long term or quickly also, depending upon thickness, depends upon the character of the soil. In all these cases now, we are looking at actually the excess pore water pressure. The excess pore water pressure has to be dissipated, and this may take, in the case of Palaceophyanotes, it's taking 100 years. In some cases, it may be very quick now. So anyway, when this is dissipated, actually, what's going to happen? The soil is now consolidated. Once the soil is consolidated, what do you mean that it has got extra strength actually? It's got more strength than when we started with now. What is happening is, initially when we did the investigation, we had the properties of the soil in situ as it occurs actually. But now that you did some bit of excavation, that means the foundation depth, and place the loads on this as foundation and then start the construction structure, now it has to develop the excess pore water pressure, and then this will dissipate in the course of time. Once this pore water pressure dissipated, excess pore pressure dissipated, obviously the soil is a better soil now. The effective stress is going to increase now. Those stress is going to increase now. So normally we're not worried about that stage. Normally we're not worried about stage. That's why we talk of, yesterday I talked of the undrained strength and then the long-term strength, that means a drained strength actually. C prime, phi prime, and Cu we thought of. This is something we have to remember now. That means at the end of consolidation, when all the excess pore pressure dissipated, the soil is going to be better than what it was now. In fact, this fact is used when using geosynthetics for foundation improvement. The second aspect of it is what we are going to say. The long-term response is the constant load now. That means the load has to be, I should say, permanently to be there on the soil as a foundation. Now, what are the kind of loads that are going to be on the soil now as the foundation? Of course, one is self-weight, on the structural load, and then also we have a live load. And then we also have seismic load. We also have wind load. Now, obviously, we want only that permanent part of the load which is going to cause consolidation. If it is going to be infrequent kind of thing, a wind load, let us say, occurring for 1 day or 1 month or something like that, it's not going to cause consolidation. It's the permanent loads which are going to cause consolidation. In the same way, in fact, the ISO defines it as service load. What is trying to do service load element, that dead load which is going to be permanent now, and that part of this live load which is also going to be permanent. That means a fraction of that live load we take, let's say 50% live load, we take it as say a permanent load now. That means it becomes service load. But now this is not going to be true. This 50% business is not going to be true when we build the IIT library building, because library building means we got racks and racks of these books actually. All the books rack actually is only live load. But then this load is so heavy that probably in that case you take 90% of the load as service load, 90% of the live load as the service load actually, as part of service load. This is something we have to remember now. The judgment we have to exercise in trying to see what are the loads which you use earlier for Bell determination, and how much of them are going to be permanently placed on the soil in order to cause the settlement or consolidation actually. So despite this, we already said, despite the low permeability, the soil will drain, of course, over months, it could be years. We already said that now. And this is going to cause, we said, reduction in the void ratio. Of course, when once void reduces in saturated soil, it's going to cause settlement. And the most important thing we have to realize is that now the settlement is caused by reduction of void ratio. What do you mean by this? Void ratio reduced because the excess pore water pressure is released by actual flow of this water to outside, to permeable layer now. So that means the volume of water which is going to be there, which is going to cause this change, which is going to cause, is going to be the change in the volume of the total soil, change in total volume of the soil now. So the change in the water volume, which is getting exited, is going to be also equivalent to the change in the total volume of the soil which are considering, the element of soil we are considering. So that is going to be very important. Now, when once is all vertical only, naturally it is leading to one-dimensional consolidation. Now we should realize that this may not be always true that the pore pressure dissipated on the vertical direction to dissipate in lateral direction also. So in rare cases, we also consider 3D consolidation. But then one of the most common assumptions which are making while using the Itasca theory, which we'll come to very quickly, is that we are talking of one-dimensional flow. The water is going to flow in one direction, in the vertical direction, and either to the top or to the bottom or to both top and bottom, depending on the various drainage layers. And the next thing we are going to do is that it is going to be one-dimensional contour, means it is going to be moving only vertical direction, not in the lateral direction. The other thing which is going to be, we have to remember very quickly, is that if we are going to place this load very quickly, the soil may squeeze out also. Those of you who have done experiments in the laboratory on clay specimens will also find that if by mistake they place a load, the soil is going to squeeze out from the you can say sandstone actually. And that means the soil has lost its strength now. So if you are placing the loads on the consolidated specimen, slowly, step by step, as per a defined load increment ratio, naturally the settlement is going to occur, consolidation will occur, settlement is going to occur. But then if you are going to suddenly place a load, the soil is not able to take the load, naturally it's going to squeeze out. Same thing will happen in the foundation also. Where the squeezing out obviously is an issue of bearing capacity failure. So we should realize this, these two are happening simultaneously. So once you are considering this now, after consolidation, I mentioned already, the soil is improved. It's physically improved soil. It has got definitely higher frictional, higher strength parameters than it was before because it's got less white space. And we also know that the particles are coming nearer now. So that's the way it is always going to be very loosely talking, stronger and stiffer. Both are going to be coming into picture now. Now that is happening in the, that is being, what you call, measured by placing the soil sample in a odometer or consolidometer, we call it commonly in India. Now, what is specimen size here now? It's a few centimeters. And maybe the diameter is going to be again a few centimeters, maybe 5 centimeters, maybe more than that now. So there are some standards to give you what is the size of the specimen. But this size of specimen, you already remember from the slide I showed you right in the beginning, that this volume of soil sample we are considering is going to be just a few cubic centimeters. Whereas in the field now we're talking of a few meters of the soil and wide nested now. So this particular small specimen is going to represent what is going to happen in the 5 to 10 meter thickness of the clay soil in the field. So naturally, if you got a very good sample, as understood as you can think of, and if you conduct the test appropriately, probably it may reasonably predict the behavior of the soil under loading. That means both the time behavior as well as the final end behavior. So that is going to be most important actually. So that's why this consultant test becomes most critical for all of us. And those of us who have been acquainted with this now, we'll discuss that also today. We'll know that even for the standard consolidation test to do, it will take at least 2 weeks if you follow all the norms as specified by researchers and by the course of practice, by the method of test given in our BAS course. Now, obviously, you can't give a result like of a consolidation test in 3 days. This is what I said. I got experience very recently from one of the areas now, very soft soil, and he got the result in 3 days. I said, oh, everybody got 3 days now. There is no way of trying to do a quick consolidation test. Yeah, there is a way of quick strength test, but then there's no way of doing this test quickly. And if you got samples from 2-3 boreholes, we need actually a gang of consolidometers. That means we need 3-4, half a dozen, so that the test can be done simultaneously because it takes a lot of time. I will not want to go into details of that, but I am just hinting you what is the correct way of doing it. Just some basic drawbacks. So once you think of it now, so what is happening is, when once you are placing this load, actually, we said immediately there is a pore pressure development now, and slowly the pore pressure is going to be, excess pore pressure is going to be dissipated, and naturally, in the sample now, if you got porous stone on the top and bottom, the soil from the center, the excess pore pressure from the center will try to migrate towards the top or bottom now. So that is intermediate level of pore water pressure. And then, of course, on the surfaces, it's going to be 0 instantaneously. I mean, the moment you have it, it's got a uniform excess pore water pressure, a function of the loads applied now. But the instant you apply the load, of course, the pressure, excess pore pressure is going to be uniform. That means same exactly from top to bottom into the middle layer. But then instantly after that now, because the top layer is touching the porous stone, naturally that pore water pressure becomes 0 instantaneously. And then it takes, of course, time for it to dissipate completely, continuously. So there is basically a phenomena occurring within the soil sample unknown to us, which is depicted only as water goes out, as settlement is occurring. So we're measuring settlement, not really the movement of the pore water pressure, because we're not measuring pore water pressure, or we're not measuring the actual water coming out. We are measuring indirectly through a change in the thickness. That is what we started with now. The amount of water getting out is going to cause you thickness change because we got a specified volume of the sample. So the maximum path is very important. In the laboratory, we always keep porous stones both top and bottom along with the filter paper, but in the field it may not be so. So if you are having a draining surface both on top and bottom now, we say that the middle of the sample, the excess pore pressure has to dissipate, it has to go travel half the thickness to the top or to the bottom. but in the field it may not be. Maybe you got only a drainage layer at the bottom only. So the path, the length, the excess water pressure travel to get released is going to be equal to the full thickness. So that becomes also a very important point for us now. So thickness required now is thickness for actual flow of water is going to be half the thickness. That small h is equal to h means the full height or thickness of the sample. What is the information we are going to get from this test now? At each stage, when we apply a small load to begin with now, we are actually interested in the time rate of consolidation. We always, obviously, take the time versus compression readings once we apply the load. And then, of course, for all loading stages, that means at the end of the settlement being measured to be not no more there, then we are going to apply second load, and of course, like that third load and fourth load, the load increment actually, and then all this at the end of this application of each load now, where no more settlements will occur within that stage, naturally, it is going to give you the compressibility of the soil, and also through the overall behavior now, we will like to see whether the sample has been pre-consolidated in the previous history. That is also an important aspect which we are going to get. That means we are going to get three kinds of results from this now. One is how long it takes to consolidate for a given load increment. Now, what is the thickness change which we are going to get now, which indirectly reflects the compressibility of the soil, measure is compressibility, and then has the soil been pre-consolidated to the pressures which are more than the existing overburden pressure. That we'll see what exactly is there. And then in some cases, there is unloading also. That means some cases, after the soil at the top, due to erosion has been removed in the field, the soil may start swelling also. That means going to rebound. The swelling is going to more if it's a swelling soil. In others also, there is unloading so that the particles try to move apart basically. So there's always a rebound deformation which is going to be there, which can be measured in the laboratory very easily. So from the kind of results we are going to get now, from the time compression rows, actually we are going to get, we can obtain what we call as the CV. CV from fundamental viewpoint now, we can think of actually as a function of, this is of course coming out from the theory of consolidation initiated by Poisson soil mechanics. So K is the permeability and MV is the compressibility factor, you can say, and gamma W is of course the unit weight of water now. So CV is the index actually to tell us what is the time rate of consolidation. So that is why we call CV, and that is going to be most important parameter to understand the time effort situation now. And obviously, there are people who use the square root of time method, log time method. Most common is square root of time, and log is of course used. The log method is actually used when it is very soft and when you are likely to have a secondary consolidation also. So that is coming out from this picture. So what is happening now? The results which you got can be plotted basically in different ways. This actual data directly. Okay, so when you plot the data, that means what is happening now? The actual data means we are plotting the root of time versus the compression readings we are going to get now. The readings are just plotted. You can see 5,500 like that, something is plotted. And from the instant of loading now, we are measuring the compression actually. We are measuring the dial gauge reading. And then we are actually plotting not directly with the resistance time, but we are plotting the root of time, because that is a, what you call a phenomenon which is observed by, in theory, by Terzaghi. So we start following that now. So we start drawing a straight line, you know all these details. I assume that you know the details actually. And we are drawing a line which is inclined at 10% more. And then wherever it's going to cut now, we say that that is going to give us the time, right, time for 90% consolidation. So there is a, we can say, a geometrical way of trying to obtain this value of time required for 90% consolidation by this gimmicks, you can say. And the same way for the other method also, using the log method. So all of both these methods actually have got relation with respect to the theory also. In fact, Sridharan from IISc, who was my supervisor also, he brought out a new theory actually, wherein we can also predict using hyperbolic relationships now. So these are classical ones now. We can do an equilibrium prediction using hyperbolic information. The advantage for that is you may not have to really do the whole testing also. There's an advantage in system. So by this process now, by this getting this T90 or T100, whatever you can think of, we can actually obtain the values actually. What is it we are going to get now? The time factor is coming from the theory of consolidation. We'll see what is it is being predicted. And then T time for a degree of consolidation which you require. That means if you say is 90% consolidation, then time required for that now. And H is the thickness of the drainage path we said now. So from this, knowing T from theory, we can get the value of CV. So which is most important for all of us actually to understand the time relationship between the settlement or consolidation in the field. We expect that now. So I already mentioned that the H is going to be depending upon the length of the drainage path. So then the next thing which we are going to look at, of course, is what are the, this is basically coming out from this now. And from this kind of test, we can also estimate naturally at the end of each load increment, we can get actually the settlement, amount of settlement. And like that, for each load increment, we are going to get the settlement. So that is what we are going to use to begin with now. But you use it with theory also. We'll come to what the theory we are going to use for this. So the theory always says the moment you apply any load on a system, we are going to have settlement now. We call it as we said now, we call it as immediate settlement. We call it as immediate settlement and or last settlement. It takes place during or immediately after construction of the structure. It's also known as distortion settlement, as it is due to distortions within the foundation soil now. In fact, in the laboratory also, the distortions do occur now. So anyway, what we are actually looking at is, I should say that immediate settlement now. It is obviously elastic anyway in the case of sands. Okay, in the case of sands, that may be the only settlement which will be occurring also. The second thing, of course, is the consolidation settlement, which is going to be there due to the dissipation of excess bore pressure, which means that gradual expulsion of water from the voids in the soil. Okay, now that is obtained obviously using the experimental data and the consolidation theory, which is propounded by Kartasagi. So then third aspect, as I told you, in some cases, in some soils now, this consolidation is not the end of the primary. That is why the earlier one is called primary consolidation. More often than not, this second consolidation is called the primary consolidation. And in some cases, even if the pore water pressure is going to become zero, even if the excess pore water pressure becomes zero, it continues to settle actually. Now, some people say it is going to be due to creep also. Some people say that the secondary consolidation, that movement is still occurring now. In any case, now this is not always significant actually. It's insignificant for normal soils. Only it is significant for organic soils. Now, most of the theories which are having are not applicable, in fact, for organic soil. So we are dealing with only inorganic soil. So if you think of theoretically, what is water settlement now? Water settlement is simply addition of the immediate settlement, the consolidation settlement, which is can say primary consolidation, and also theoretically second consolidation, which more often than not we don't consider because we are not normally dealing with organic soil. So that means we are only going to have the initial settlement or immediate settlement and the secondary and the consolidated settlement. Now there is also scope for the settlement due to many other causes. In some cases, they may exceed whatever we already thought actually. It could be such a collapse of the soil. So there are certain kind of soils called collapsible soils. So unless you're dealing with them now, this may not occur always. Also, sometimes the underground erosion piping can occur below the foundation. And also it occurs due to lowering water table now. Lowering water table actually increases the effective load on the structure, on the foundation soil, and that actually can cause settlement now. This can be theoretically calculated, and most of you who are teachers give questions also on this for assignments or for exams also. And sometimes thermal changes. Suppose we got some workshops which are going to produce heat now. So the water is going to evaporate now, there is a problem. And in other cases, sometimes the consolidation will not occur if it is cold storage. And also due to subsidence of the total area. That means, in places like Dhanbad and other places now, due to the excess mining which is done below the ground level now, the entire city or township is settling actually. It's called subsidence. Subsidence can also occur in the city also, wherein there are cavities due to lime actually, due to removal of lime actually by action of you can say rainwater, and because this carbonation, all of them are going to maybe sometimes cause these lime caverns. And in a place like Delhi, they were also found to be caverns just below the road sometimes. And also, in fact, one of the leading structures in JNU, the famous JNU in Delhi, we find that when they're constructing houses for, the residential apartments actually, we found there's a huge cavity just below the foundation. So all that was due to, in the early days, there used to be a lot of, material which can be excavated for mining kind of thing. And so that mining actually caused a lot of issues now because that mines were not filled back now, so cavities remained there. And so that caused subsidence because we constructed foundation on that. So that is also, you can say, site specific. It's not going to occur everywhere now. So we should also look for, when I said we are going to recognize the survey, we should see where we are going to have this foundation, which locality, and what is the experience of the neighborhood structures for foundations is occurring due to this or not now, because loading water means, for example, the area I am residing in Hyderabad now, probably I was the only house within 100 meters. Now I have so many houses in this. I mean, 100 houses are built last 10 years actually. What is happening now? Each house has got its own borewell. So much pumping of water is being done. Had it been in alluvial soil, this one, my house could have sunk actually by a meter. But then luckily we are on rocky strata. So there is a water table lowering anyway, but lowering has not caused settlement. I was not worried about that, but I'm just telling you, had it been in a coastal area, naturally the houses could collapse also, could sink also, could also different settlement also. So these aspects are to be given as much importance as sampling and calculations of the settlement now. And it is due to these and many other reasons now, whatever value you are going to calculate by any theory, maybe off the mark by sometimes 2-3 times. That means the settlement you are going to calculate by the theory could be much, much less or could be much, much more than calculations, than the actual observation. So now the result which you are going to get now by taking the settlement readings or what you call settlement of this soil sample in the consolidometer now. So we can plot with respect to what is it we applied, what we call as effective consolidation stress actually, because we are taking the measurement of the thickness at the end of loading, at the end of consolidation of the loading actually. So that is going to become the effective stress or effective consolidation stress. And the other direction, we are going to talk of a strain. We can talk of a strain also. That means settlement divided by the thickness. That's one way I'm doing it now. So if you plot directly like this now, this curve will be something like this. Now, very rarely you plot this. You always plot actually the effective consolidation means effective stress versus void ratio, which is easy for us now. We talk in void ratio terms because that's easy for us to calculate the settlement. Otherwise, nothing else. So when you do this now, so we get a kind of curved kind of behavior now. And mind you, this is not always going to be in the linear scale, it will be in the log scale also. So anyway, if you plot like this, it will be, one is of course, we got percent consolidation, that means percent vertical strain, and then we got void ratio effective stress actually. So that is what is the kind of picture we are going to get now. So this we can have a direct kind of behavior, or we can also plot, we plot versus the log scale. Mind you, the picture earlier I have given you is on the red scale actually, linear scale. So this line actually, whatever curve we are going to have is definitely curved. Okay, this is the consolidation or loading, and this is unloading. So unloading means obviously when you are reducing the load now, it also rebound. That's what happened actually. It was here at the end of consolidation at the say 80 kPa, and then when once you reduce the load to 20 kPa, 40 kPa, it has started rebounding, and then finally at the smallest loads it also swelling much more than what we thought actually. So this is total consolidation behavior in the linear scale. Now it's more convenient for us sometimes to plot in different scale also, but the slope of this actually we define as AV on the linear scale now. And what do you find in this case is AV is not constant through and through. It is also different actually throughout this. This is what we have to always keep in mind actually. So AV is a definition of this curve basically on the linear scale. Okay, and then by some conversion divided by some 1 plus E naught, then it becomes MV. Okay, so this basic fundamentals we have to remember. Now if you plot void ratio versus log of the effective stress applied, then this line actually becomes, this entire line which was covered in one direction is becoming a different kind of curve. So once you are doing this now, so we seem to have sometimes this kind of curve now. So this behavior is distinct actually. This behavior is distinct basically from many different angles. What is the angle which is going different now? We find that there is a change actually in this. That means up to this you see that the amount of void ratio change, in this case vertical strain, and then I'm plotting here and this is void ratio. So whatever it is, ultimately the strain is not changing much or the void ratio not changing much, up to this value. And beyond this, it seems to be decreasing at a very fast rate. Now keeping that in mind now, so the slope of this line now, the slope of this curve at any given point is defined as CC. compression index actually. So the AV and MV refer to the linear scale and the CC refers to the log scale. But I want to show these pictures to you for the simple reason that the CC also not constant. It is actually changing continuously. The CC was very much less here and CC is going to be much more here now. It changes continuously. It is not a line. It is a curve actually. So a lot of people actually keep just giving some small range and let's say the CC or give one value only. So I would personally prefer to, if you want to assess any foundation case now, I would prefer the complete curve. I will also tell you the reason for this now. Okay, not numbers, but the full curve, what we call as consolidation curve. Okay, or ELOC curve we call it now. So when once you are looking at this now, why the change is occurring now? By common sense, you can say that, yeah, this sample seems to be behaving very stiff up to this point, and beyond this, it is becoming as well soft now. So maybe something has happened up to this level in the sense that maybe it has been consolidated earlier to this kind of effective stress. That means the soil was already made stiff earlier before you went there. So that means existing overburden pressure and the past overburden pressure, these are the two differences you are going to consider. And in this case now, beyond this, naturally, it is a kind of fresh loading being applied. That means virgin loading being applied. First time the loading is applied. So this change is what we want to find out. And this is what we now define as a pre-consolidation pressure. Okay, so we are getting the slope of this or this portion of it now. And then we are getting the rebound values also in terms of CC, MV or AV, whatever it is now. So the point is that we are going to get the total consolidation behavior. That means how much settlement will occur at what kind of loading is what we are going to guess from this ELOC because, and that is going to be the basis for all our work now. So when once you plot the same thing now, we already said that, for example, without much consideration, I have taken a sample from here, let us say. That means at this pressure now. So that is here. Now I know from calculations of the loads which are going to place on the foundation, and then the stress coming at the level of the layer of the soil which is going to consolidate. What is the stress? I calculate by theories, we'll come to that now. So once you calculate the stress is going to come, additional stress is going to come because you have placed the loads or because you place the foundation on that now, the stress could have become this much. Okay, so if I just go back on this line now, earlier the void ratio was this much because that is the existing overburden pressure. And you are going to apply additional load now because of foundation construction up to this now. So the difference between these two things, the difference between these two values of void ratio is simply giving me the strain. The strain deal in this case means it's a delta H or H. H is the thickness. In a sample which you need now, it is sample thickness, the change in thickness of the sample which you tested. In the field now, the H is going to represent the thickness of the strata and delta H is going to be the settlement now. So basically, by just looking at the change in void ratio between these two pressures and then knowing the value of E naught means this E naught. This is what we started with now. This is what we started with, the void ratio, initial void ratio. So by just knowing the different things and the initial void ratio, and we are able to get actually the value of delta H by H, and that means just multiply this value by H now, we are going to get thickness. We are going to get thickness change or consolidation. I like this basically. I have no more calculations, no more AV, CV, MV. I just know these two things. So I'm able to get the change in void ratio. I already know the initial void ratio. I'm able to estimate this now. Directly, the delta H coming out of this equation. H represents the thickness. Now, if it is one single layer, it's okay. Otherwise, we always subdivide this thick layer of thick stratum of clay into many layers because distribution is though uniform, but it always gives differences. So I would like to do multiple layers actually, even if it's a single layer, divide into different layers or different thicknesses and then calculate it. And the thickness of this each layer is going to be smaller near the foundation. And then as you go deeper and deeper, I make thicknesses larger. Anyway, so the delta H you are going to get will be summation of the thickness change for each of the layers. You are going to assume whether it's naturally different or artificially made different by dividing the thick layers into sub-layers actually. So this is simplest I like actually. There are no more values which are going to require. I just require the ELOC curve. That is the one way of looking at it now. The other way of looking at it is going to be, I can also get the initial values here before the so-called pressure-free consolidation, and then CC here as well defined now. So all of them can be obtained by the indices actually, by the slopes now. So in this, we come back to our definitions now. What is going to come out now? of these curves because it's a reflection of the what we call as stress history of the soil now, stress history of the clay soil now. So we are talking of NCC meant actually normally considered clays. We are talking of clays now. So you can have normally considered clays, we can have over considered clays, we can also have under considered clays. So to begin with now, if you want to define this, a normally considered soil is one which had not been subjected to a pressure, we'll say overburden pressure, effective overburden pressure, greater than the existing overburden pressure. That means if the soil has been laid by sedimentation or geologically, and the layers remain there for millions of years, and so each of the layers you are going to consider is going to be normally considered because subjected to consolidation under the existing effective overburden pressure. So all the layers now are going to be obviously normally consolidated clays. In the other case, what happened now? Probably geologically, the soil has been sedimented, each layer is fully consolidated because some millions of years elapsed. But due to geological changes now, maybe the top 100 meters is eroded. Okay, then what's going to happen now? The soil which is not eroded has been consolidated to a thickness which has been eroded now. And today we find this is thicker, we find the stiffer stratum, stronger stratum compared to earlier case now. So it is that soil which we defined as it's said to over consolidated if it had been subjected to in the past to a pressure in excess of the present pressure. So this is what we try to determine actually by conducting the test. We'll come back on this again. So this is what we're trying to say. This sample has been stiffer up to this layer, up to this part, and then has been softer beyond this part. So this is, we can say, is the pressure which is obtained as the what we call as pre-consolidated pressure now. Now higher is this pressure, naturally, the soil is going to be more over consolidated. We'll see that also. So then we come to the third aspect, which is not used actually, but in offshore structure, this becomes very common in fact. So what is happening is, under consolidation occurs in soils that have recently been deposited. I will just give a small side story to you. When we were investigating the offshore deposits of gas actually, both in the Krishna and Godavari basin, which are now very popular sources for all our gas actually, when the investigation was going on, the initial vehicles, initial ships actually, initial barges which are investigating, they are only barges to investigate the soil profile actually. What was happening was the strata of the bottom of the river, the seabed actually was sort of kind of flowing now. What do you mean by the soil strata flowing? After all, the strata was only at hardly an inclination of 4 to 5 degrees only. That means slope of the angle of 4 to 5 degrees or less than 10 degrees was actually moving like a slide actually. If you go back to the history of this now, if you try to see how much sediment is coming out of the mouths of Ganga and Brahmaputra near Calcutta or near Bangladesh, what we find near Bangladesh, I mean the boundaries between these things, what we find is that the amount of sediment is coming out is something like 500 million tons, 550 million tons per annum. This much sediment is coming through the mouths of both Ganga and Brahmaputra. The nearest value to this is 350 million tons in Gulf of Mexico. That means we have got the largest deposits of soil sediment coming into the sea. Now that is coming there, but over the years now, it is simply passing by and slowly moving towards the south of our country. And naturally, every year this is occurring. So if every year the deposit is being deposited, what is happening now? More and more soil is being deposited, more and more soft soil is being deposited, more and more clay soil is being deposited. So the bottom strata is actually, though it was draining, though it was going to consolidate, but the rate of deposition is actually increasing more than the rate of consolidation. So that means the soil is becoming under consolidated because what means that the clay layer has not yet become to equilibrium under the weight of the overburden load. In one of the conferences held in 1980s actually, Professor Gulati and his colleagues calculated this rate of consolidation also and said that the more the deposits, that means over the years now, the soil is likely to be more and more under consolidated. That is unfortunate actually. That is why the slope stability is a problem now. And we know that there is a lot of gas there, a lot of other issues are coming out, but it's one reason now. So the people who are in the initial stages, they simply went away. They simply closed the shop and then pulled up their legs and then went away because they're worried about this failure of the barge actually, which was of course places, legs are placed in the seabed actually. And that is because of the under consolidated soils which are there. And that is because the flow, this mud flow actually is occurring at as little slope as 4 to 5 degrees. So it's not a theoretical concept, it is an actual concept which is there in our own shores actually. I should say shores very near, you can say Visakhapatnam also. So that is the thing, the equilibrium has started to come now. So war consolidation occur, of course, I mentioned already, due to either a change in the total stress or a change in the pore water pressure. Both changes would alter the effective stress. So geological deposition followed by subsequent erosion is an example of a change in the total stress that will pre-consolidate the underlying soils. So if the line is only one single line, naturally the soil is essentially a normally consolidated soil, normally consolidated clay. If there is going to be a slope change, actually, that shows the soil is over consolidated, or that shows the pre-consolidated pressure now. So naturally, one thing we should remember is the normal consolidated clays and over consolidated clays are not different types of clays. They are the same kind of clays. It's only the condition of the excessive water pressure dissipation which is going to be important, which causes pre-consolidated to occur now. So the causes we have already seen. So the maximum pressure to which an over-consolidated soil had been subjected in the past is known as pre-consolidated pressure now. And this is what is happening. We already said that actually, and we define this. I already mentioned all the things now. So pre-consolidated stress is the maximum effective stress which has been applied to the element of soil. And over-consolidated soil is current effective stress is going to be less than the pre-consolidated stress. And then over-consolidated soil is actually consolidated at the current effective stress. So pre-consolidated stress equal to effective stress. So that's a single line only. So this is the basic issue which we are considering, and there are a lot of methods to do this now. There's a cascade method and things like this. So all of you are familiar with those methods, and we can also decide upon this now. In fact, the best way of doing it is repeated testing and not the conventional way. But anyway, there are simple methods of trying to obtain this. I think as teachers, you're familiar with this kind of procedures, and these are all empirical procedures to define these values. So then we already defined, apart from the pre-consolidated stress now, which really means that if your now present loads are going to be lesser than that of pre-consolidated pressure, you will have lesser settlement. The present load which are going to impose due to the construction of foundation is going to be more than pre-consolidated pressure, natural settlement is going to be more. This is something we have to do. It's not in our control. It's a structure which we make now. If the structure demands higher stress, actually, obviously, we are exceeding pre-consolidated pressure, and that means settlements are going to be more. If you are going to be below the pre-consolidated pressure, naturally, the settlement is going to be less. Yes?
Yes,
Any
sir.
doubt?
Nice presentation.
Hello?
Nice presentation, sir.
Are you able to hear me?
Yes, sir. Nice presentation.
Thank you. So then
Thank
coefficient of volume change is, of course, we are defined MV and other things now. We are familiar with this. Basically, we said AV is the slope of that now. Slope of that linear, both void ratio and pressure. And AV divided by m plus E naught is going to be MV. So they are only simple relationship of the slope actually. Okay. So after having got this now, we can always calculate by using the plot as I mentioned. And we also find, of course, it's also mentioned in our report, unfortunately, that if you can't conduct a consolidation test for pure estimation purposes, for a preliminary estimation, we can also use the relationships which are there. This is as old as second peg, long ago, 3 decades, 4 decades back, and CC equal to function of liquid limit, and also this is function of the initial void ratio, this is void ratio, and many things are there, but I desist you from using this because these are only pure empirical relationships now, and we can't use this for submitting settlement calculation in our present structures for which you are doing estimating now. So these are pure guidelines only for guessing initially what kind of work we are going to do. So then, of course, as I told you, we can use the equations or we can directly use the void ratio change actually and then calculate this. So these aspects we considered now. And we already said that for NCC, it's going to be a combination of initial and primary and secondary settlement. And all of them are, of course, today well known. We'll quickly skip to that. Then comes actually, we are calculating the stress change basically. Now, to calculate stress change, we can always use theories. We can use the business theory, we can use the White theory, we can use Bumster theory. But the point is that whatever theory we are going to use, we know that basically, fundamentally, that the load which are going to place near the surface of the ground is going to distribute in form of a bulk basically. Okay, so this entire soil is going to contribute to the number one settlement. And then, depending upon the kind of situation now, the thickness of the soil, which is main influence, is going to be varying also. It depends upon many things. It depends upon whether it's a spread footing or a strip footing. And naturally, we can really try to see the influence of this. So if it is strip footing now, we find that the influence is going down actually, up to 4B. And in this case of a spread footing, it's only going to 2B, essentially B is the width of the footing. Now these you can also calculate and prove yourself also. You don't have to go by theory only. But then it's difficult to calculate the bulb because shape is not so clear. So people assume actually as though the distribution is going to occurring in a trapezoidal form basically. And 1:2 is a very common way of doing it. And if it is a footing, spread footing, let us say, so naturally it is spreading on all the directions now. So the B will become B plus Z and the L will become, or this also will become B plus Z actually. Same thing is going to happen with strip footing. So strip footing, as you know, is something like a plane strain. We will see that also later. So the point is that one has to consider this kind of distribution for simplicity. This is not perfect now. Okay. So once you do this now, if our layer is somewhere here in between, naturally we will find out what is the stress change occurring now. Like this, what is stress change occurring in this now. The other important thing which you have to always remember, which you have said right in the beginning itself, is that if the foundations are going to consider small foundations like this, now let us say, the zone of influence is going to be this much only. If you got a large foundation like a raft now, zone of influence is going to be so much now. So having a small foundations quite near each other is not going to influence, is going to influence in a major way the settlement also. And if you do calculate as the individual settlement is occurring, individual settlement of each column or each foundation is occurring, it is actually wrong because they are so nearby that they will act together to cause a settlement in the entire pressure bulb actually. In the same way here, we can also see that now in stratum 1, there is a distribution now, and this top layer is going to be, top portion of it is going to be nearer the foundation. We will have a thicker layer, a thinner layer, and as you know, the stress is decreasing as you keep going down. So maybe I'll have a thicker layer here now for calculation. So it's never calculated as though it's going to be one single layer. It will be divided into multiple layers because the relationship is not linear actually. So we should divide them into multiple layers now, whether it's multiple layer or not now, so that we get an accurate value that is most recommended. I'll repeat again, the layers nearer the bottom of the foundation are always assumed to be thinner. And then as you keep going down, we can assume thicker layers also, even if the soil is going to be same kind actually. Otherwise, of course, we already have the extreme one now. So, which obviously means that we are going to have conservation data for each of the kind of layers which are going to be there. That means, okay, number stratum 1 in this case is maybe sandy soil, but stratum 2 could be different than stratum 3 and stratum 4. So we ought to have conservation data in each one of the layers now. That's very important. Just taking one sample in one stratum is not going to give indication because these soils are very different now. No, this is something means that for the same borehole, you have to do a number of constellations to be able to get a field value. So then we can always calculate what is the settlement actually by the elastic settlement or vertical settlement now. So that initial settlement or immediate settlement or a settlement is going to be function of the what is the kind of load which you are going to have and the width of the foundation which you are considering, and then mu of the soil, and then modulus of the soil, and then influence factor which is going to be considered. So influence factor coming from theory, rational theory anyway. Okay, but then mu, again we are going to assume. E, of course, we need to conduct a fractional test to find out the slope of the line actually for each confining pressure. And then Q is something we know. B is what we're assuming to begin with now. So the vertical settlement can be obtained by the using this formula, which is the formula, and then of course our standard, which we are using IS 8009, gives you that values also. So this is a common reference to all of us now. It's being revised continuously, and we can calculate the settlement based upon DCP, diamond penetration test also. We can do on many other things, SPD also. And for this actually, if you're using SPD, then this is the curves. Probably you're familiar with this curves also. So on this axis we have the width of the foundation, the settlement now for different kind of foundations. Actually, this is again on the log scale. You should realize this now. The vertical axis settlement is on the log scale, and the correction factor for water table is also given clear now. So what is important to is that this is 10 to the power minus 1 and 10 to the power minus 2 settlement in meter per unit pressure. That means per each kilogram per centimeter square is giving you. So you see that now when SPD value is low, naturally the values of the settlement initial settlement is going to be more, and as the n value is going to be more and more, natural settlement is going to be again reduced by one order. So the order is important. This is one log scale and the log scale actually. So this is what we have to remember in terms of this one. So obviously this is only settlement that occurs in the sandy soils. Okay. Now we can also calculate the constraint settlement examining using the same theories. And as I told you, unfortunately, the code also gives you the approximate values of CC, but I will resist you from using this because this is only a pure estimate based on experience, nothing to do with the soils which are considering at a given site. Okay. So this is giving you clays now. In clays, one way of looking at it is that, for most practical purposes now, when you conduct consult test, we are going to draw that line actually, is it not? So the initial portion is going to be considered as immediate settlement. So when you do this settlement actually, in most cases, I for one will take the settlement which are calculating by the theory, because we are only going to change from between one load increment to other load increment. I will take it as a settlement of the consolidation as well as immediate settlement. That is way of in which most people do anyway. So for all these kind of cases now, the bottom could be, it could be very thick layer or it could be thin layer now. So the values which are going to which I'm going to get now for a cohesionless soil, we are going to consider also the effect of the H over B. So for which the lambda value, we are going to take this now. So what is this represent? This is going to give you pore pressure coefficient. What is pore pressure coefficient now? For this, we have to conduct a traction test actually. In a traction test, what you are going to get, we are also, traction test means we are going to conduct a CU bar test, consolidated undrained test with pore pressure measurement. When you do that now, the pore pressure being measured, of course, still beyond failure also. So we have the pore pressure measured in a CU bar test at failure, and we also know deviated stress at failure now. So the pore pressure value at failure divided by the deviated stress at failure is going to give you the value of pore pressure coefficient, Kempton's pore pressure coefficient A. Okay. So that value, they say, is going to be usually for NCC, it's going to be between 0.5 and 1. And for over-concentrated soils, it's going to be less than 1. And then, of course, under-concentrated soils, sensitive soils, is going to be between 1 to 1.2. So they have given these values actually for finding out the settlement coefficient lambda. And this lambda also depends upon, obviously, the shape of the foundation, circle and strip. This is what I defined now. And so this value of lambda we have to interpose in the settlement we are going to get for the cohesion soil. So then, if you can't conduct a traction test, obviously the code gives you another view. So they say use these values now. So for different kind of materials, it is giving you the same range actually. So that is what we are going to do. The immediate settlement beneath the center of any load area is of course known to the same equation I'm giving you, and they want you to assume actually 0.5 for clay, and there is influence factor now. It depends on the L and B, and this table also is given from the same code actually. Influence factor, where which kind of foundation we are going to have, which kind of shape, and at the corner and the center, and of course average they are giving you, and so we can always determine the immediate settlement for clay also, and this needs to be corrected also depending upon finite thickness actually. So these corrections are also done. These are actually known as the Steenberg's influence factors. So this is also part of the code. I don't think I will go into detail of this now. So also we need a correction for what you call as for depth actually. So this also is given actually for rigid foundations is given you, and these values ultimately depend upon again the shape essentially and the depth of the foundation, which I am proposing now. So this correction, which is called as false correction factor, this also the chart is also given in the code. So I'm not going to emphasize too much on this now. So then finally we got the immediate settlement, plus we can calculate what is the settlement at a given time also. So given time means naturally we are calling a 50% degree of consolidation, or we can find out again within the time, that's T part of we can introduce now. That means take it as a degree of consolidation is a function of time factor, or within a given time how much consolidation occur we can find out now. And the same theory which is proposed by Terzaghi is used consolidation theory, one times consolidation times settlement now. And this of course is the original curves by Terzaghi for different isopropyl distribution. We're looking at the topmost curve, and that gives you a UT relationship, which is simple. Which is simple now. This is for propyl distribution, isopropyl distribution. It's same from top to bottom now. This is the most common thing we are trying to use now. So if you say that I want to find out for what the amount of consolidation occurred now, I can find out that, or I want to find out time and how long, how much settlement is occurring. Both ways you can play with these equations and then get an idea of how long it takes settlement or how much settlement is occurring in a given time. Both ways you can try to do it. So the only thing in the rest is going to be what kind of, most important, of course, part of it is going to be the distribution, how the stress of the foundation is going to be distributed over the layers now. So what the recommendation of our code is going to be that we use business theory for normally constructed clays now. For raw constructed clays and laminated clays, we use Westergaard, and for sand, we use Florish equations, but most commonly, we use only business. So like this, for different deposits, we can try to use it now. So this is based upon all the common things we are going to do. And we had also the numerical charts which are going to be given for this now. But today, we don't really go to that because we got simple numerical solutions available for us now, or we can develop Excel sheet for this now. So all this brings to our calculation of the settlement for a given load, for a given pressure, which you are going to think of. So let us say using the allowable, I can say safe bearing capacity values. So how much settlement are we going to allow now? That, of course, is known to be a function of the type of soil, type of foundation, and the structural frame which are going to use for the structure. And the limiting values can be anywhere between 20 to 300 millimeters. And the IS code on foundations actually, there are two codes we have used now till now. We use the one on bearing capacity, we use the one on settlement calculations, but there is another one which is giving you actually how to design foundations. So in this now, apart from the total settlement, it also gives you the different settlement now. So that is the code actually, straight from that code. And what we are finding is for different ISO foundations for steel structures and RC structures, grout foundation for steel and RCC, sand and clay, plastic clay. So we have got the maximum settlement, advanced settlement, and angular distortion. So it requires a lot of time for me to explain all of them now, but we have to play with these things actually always. Depending on the kind of structure now, we have to see what is the maximum settlement. So maximum settlement means the total settlement actually. Now how to calculate different settlement now? Different settlement between the adjacent footings, you can say. Okay, now that depends upon obviously what spacing between the columns. Okay, now certain structures are more tolerant to different settlement. So the distortion which is allowed, let us say, in a steel structure is more than what is on the RC structures. So all these common sense we are going to use. All these values are only based upon experience. There is absolutely no theory behind this. And you will realize that now the settlement we are going to allow, let us say for a raft foundation, is as much as 100 millimeters in a plastic clay. Okay, and for the same raft now, sand and hard clay, we are allowing 75. So all this is based on experience only. For normal foundation, we say 50 millimeters to 20 millimeters. So now if you got different columns having different loads now, and they will have different loads, naturally they have different size of footing now. And so naturally adjacent foundations may have differences in the settlement values. So we are looking for now not total settlement, we are looking for different settlement and the distortion. That is something very important. So these guidelines for this are given in IS 1904, affirmed again in reaffirmed in 2006 now. So some aspects we have to see. It gives you the reasons for how to locate the depth of foundation. I'm not going to enlist this now, but one should go through this code because it's very illustratively they have mentioned what are the ways in which you define the depth of the foundation. The first thing, of course, is securing of adequate allowable bearing capacity. What do you mean by this now? If you keep going down in a C5 soil or in a F5 soil, our bearing capacity is going to increase now. It's not going to increase, of course, for a pure clay. That is something we have to remember from our calculations earlier. So if you got a F5 soil, let's say C5 soil, naturally, the more depth you are going to have, the bearing capacity is going to be more. So we may have to go deeper to increase bearing capacity. And then other things are anyway there. Other reasons are there, I mentioned. One has to go through this now. And then what about the loads now? In terms of loads now, we already know actually, we have the dead load, we have the live load, we have the dead load plus live load plus wind load plus seismic load. Okay. Now, which part of the load we are going to take actually for calculations of the bearing capacity as well as, of course, the settlement. It's very important for us to look into this. So as the code says now, live loads from the floors above as specified in so shall be taken in proportioning and designing foundations. Where wind or seismic load is less than 20% of that due to dead and live loads, it may be neglected in design. First combination of loads shall be compared with the safe bearing load to satisfy the allowable bearing pressure. So like this, they are giving details now. One has to go through this now. I will illustrate only what is going to happen with respect to the settlement now. So settlement, as we already said, elastic compression, consolidation, groundwater leveling, seasonal swelling, ground improvement on earth slopes is required sometimes, and then or ground change, and other causes, intestinal excavation, mining subsidence, underground erosion. Now, when this code was written, probably the problems were not there. Today, all these problems are occurring. There are cases when the building settled because of lowering of water table, because of excess pumping. There are many cases right in Hyderabad, actually, which are familiar with, maybe in Visakhapatnam also, wherein the adjacent buildings, actually, when we are trying to go deeper, new construction, the existing buildings actually are having distress. And so this becomes very, very important for us. Many failures, I remember, occurred also in maybe in Bangalore or in Visakhapatnam and in Hyderabad. And it has to be prevented by doing many other techniques, gimmicks, and which are very expensive now. And also, we know the problems of black soils now, the swelling and shrinking clay, and tree plantation, these others are affecting in a big way. So the point is that please don't take this as a list of things now. These are becoming relevant today, and we have to consider this now. They are not present in form of an equation, and because they are not present in form of an equation, we can't afford to neglect it, and there's only going to be unsatisfactory results. The other point I have tried to mention was, when we got adjacent foundations now, naturally, there is a possibility of a different settlement occurring now. So we can't afford to have this much different settlement just because the column loads are different. Column loads are going to be different because the central column will have different kind of load, the outer columns have different kind of load, and also the columns underneath staircase and of course lift is going to have different loads. So this is unavoidable actually. So to manipulate this, let us say, there is a criteria given by the code itself actually. What it says is that we try to, which is reduce the different settlement due to live loads only. So what we are going to do, we take for fine grained soil, the settlement shall be estimated correspond to permanent loads. There is no problem at all. Dead load and all fixed equipments are considered as permanent. Generally, one half of the design live load may be taken as being permanent. This is what I said. If you go to a live load building, it's not 1/5, it may be 3/4 also. So that means permanent load is going to be the dead load plus part of the live load. So that is what is now defined as a service load now. So in the service load now, what do? We pick up actually a column, determine the required bearing area for a column having the largest live load to dead load ratio. In the conventional method of design, what is happening? We got allowable bearing capacity, and we got this dead load plus live load for the maximum this one, and then we are determining the area for this. The design area for the foundation. So compute this for the same column, the design bearing value. What is the design bearing value now? It says service load divided by the A. So that is going to be our design value which we are going to use. So determine the area for all these other columns by use of QD, that is bearing area equal to service load by QD. So that is the method they suggested now. Hope it works, but definitely is better than anything else now. So there is a change which we are going to call for. Now the other thing which you have to remember, of course, is two things now. Whenever you are going to have a single column or something like that, and the top soil is hard, naturally, if the foundation is going to be near the surface, yes, the failure plane is going to be within the hard soil. But if you got naturally a deeper foundation, this failure zone can also get into soft clay. So that is leading to problems. Okay. Also, we have the at least name-wise what we call floating foundation. What is floating foundation now? We are just going down one basement or two basements now. So the calculation requires, says here actually, it just calculated roughly, of course, it's not in units now. This picture is taken from Bernard's book on foundation engineering. So what you find is that in feet units now, you go down 15 feet now, and we have so many floors, what we are going to do. So he finds that by lowering this entire structure by 15 feet, he is going to find out that we are not placing an extra load. In fact, we are lowering the load itself now. That means we got a free bearing capacity. So that is what we have to really see. But the construction sequence is going to be very important for us now. It's not just calculation now. So one has to see now the basements are going to be useful in terms of reducing the actual load on the structure, actual load on the foundation soil. And sometimes by, particularly some of the hotels have got large tower structures actually. These large tower structures maybe it's worth having two basements, and for other lesser floors, naturally we can have one basement. So this decision we have to make it now. Now, usually today what happens is the structure people or architects have already decided what kind of structure and say, now we calculate bearing capacity. Now that is going to lead to distortion in many cases. Now, or naturally leads to more expensive foundations. So if there is a possibility of working together, the civil engineers, the architects, in advance, not asking for a report, joint report within 2 weeks of is giving the order for what do you call order for investigation. If he is able to work out what is the in advance investigation, and then he can rework out the floors in such a way that basements and things like that can be considered together now. Some cases can also have a block actually like this now. That means the whole thing is going to work as single block. It depends upon many things you are going to do. And so the structure variation can be there out of this now. Then there are many other things which you have to look in a classical way. Classically, if the foundation bed capacity is not sufficient, we have to change the foundation. That means from shallow to deep we go now. Or we provide adjustable transition between the soil and the structure. Now, I told you, like in the Palace of Fine Arts in Mexico, there are people who also put, you can say, some kind of systems at the bottom now, like jacking actually, because we know that the soil is going to inevitably settle large extent. So they provide actually kind of jack up actually. So automatically it will keep jacking up the structure. Of course, it's a design structure. And we considered actually change the superstructure. And then we say change the soil. Change soil means we change the location now. Now change the location was an option earlier now. Today we can't have anything because the land is premium now. And once you got the land, you want to use it for building a bridge or building a metro track or building actually multi-story buildings or you can say commercial buildings now. So change in soil is not appropriate. Yes, you can change the soil behavior by improvement. That's what probably Professor Madhav and I will deal with towards the end of this entire FDP. So it's not change in soil means change the location here, but then it can also be sometimes ground improvement may help sometimes, though it could be slightly costly or time taking. This is something we have to remember now. So this is what we said actually when we started with now. This is the same Palace of Fine Arts, which has sunk more than 4.6 meters in 100 years actually. So it is still sinking. So the result is that now when we are going up the staircase, up the steps for the portico now, we are actually taking steps to go down. All the parking lots, everything is in a reverse way now. The parks are parked in reverse way actually. So the point is that the structure as such is fine, but the aesthetics is gone actually. They have to reword everything. All the electrical lines or water lines or sewer lines, everything has changed. So that is the beauty of the structure. Structure is intact, but then it settles so much and continues to settle now. And if that is going to happen now, obviously, even the roads, everything else is going to be changed actually. All around the structure is a point to be noticed. In Mexico, very special case in Mexico, settlement is going to move. Other thing which I have to say, when you have large structures, huge structures, I mean, 100 meters and 20 meters wide and things like this, all the modern colleges, all the so-called private colleges, natural self-financed colleges, they have huge structures. Now, if they are on clay, what's going to happen now? It is going to give us a distribution like this now. So there is a bowl-shaped settlement now. So what's going to happen to the tracks here? What's going to happen to the entire settlement now? And if the soil is not uniform, that means thick somewhere and thin somewhere else, naturally it leads to uneven settlement actually. And if you also got a neighborhood tower or something like that now, naturally that is going to tilt actually. If that happens to be for a bridge foundation, naturally, if this abutment is going to move this way, the deck slab is going to fall down. If the abutment is going to move towards this bridge, obviously there is stress being created here now. So that is something we have to remember now. So the problem either way now. And in this kind of cases now, what is going to happen? Naturally, the entire structure is going to crack like this now. Okay, and it may also compress actually. The compressed stress will be coming out, and here the crushing will be happening, and then cracking like this now. And also, if it is a structure like this, I mean, if it's got a frame structure now, there will be cracks at the sides also. And if the movement is other way around, this kind of thing happens in Sterling soils actually, we find cracks like this now. Now this happens due to the continuous change in moisture content and deposition of water here. Many things are happening in the blackened soils. You find that it's not just calculation of the settlement for individual footings. It is going to be total structural performance of the entire structure, and things like this is going to be very important for us. So I thought, gentlemen, this is what I wanted to cover in principle. And at the end, I want to thank our salutations to our Guruji, who gave me the energy to talk to you for a number of hours, and inspiration which is given by all of you, together with Professor Satyendra Reddy, who gave me opportunity to present these things before you. So at the end, I would like to, if you got time, I will try to address the some of the issues which are raised very nicely by one of the participants, I think Ravi Kiran Anjala. Let me just see what are the comments and see that now. Now, Ravi Kiran is a structural engineer, and obviously the way in which the structural engineers look at solve problems are different. The angle at which they look at. They think it is going to be very simple, but things are not simple now. Now, one question, the first question he was asking is, I will just read out what he said. How does a geotechnical investigation estimate the variation of the mechanical behavior of soil with time? To repeat it, how does a geotechnical investigation estimate the variation of the mechanical behavior of soil with time? I think we have just listened to the lecture now. With variation in time or the mechanical behavior is what we're measuring actually in our test. Variation with respect to time is with respect to dissipation of extrapolar pressures, and that is what we said in the traction testing we have done yesterday. So that is the way in which we do the measurement time. Once the extrapolar pressure dissipated, unless there is a change in water table now, the behavior of a structure remains same. The mechanical behavior remains same unless there is something else which is happening. Then we also have, I think, related question actually. I think let me read out now. Yeah, on slide 41 of yesterday's presentation, you mentioned that the presence of water doesn't affect sand. I hope that statement applies only to gravity loading. I think that's common sense to all of us because we are actually considering static loading only. Okay, that is gravity loading means yes, gravity loading. But then, if it is going to be earthquake loading, it's different. We know the sand is supposed to be liquefying actually, particularly if it is water table is high and the soil is, let us say, fine sand and coarse silt, there's a problem of liquefaction. Okay, so we're not addressing that question here now. So sand definitely will liquefy under some conditions with a less overburden pressure and water table being high and fine sand and coarse silt, it is going to liquefy definitely. Okay, so we are referring to static behavior. In static behavior now, whether water is there in this or water is not there, the behavior of sand remains same. That means water table change is not going to cause any change in the strength of the soil. It will, of course, water table movement is going to cause extra load on the foundation. That is what we're going to bother about it. Then he also had a lot of questions on, sorry, just went back. One second. Yeah, then he has got a question on, sorry, I lost it. One second. Yeah, what kind of test is fit for what? Is it stress control or strain control? Now, the majority of the testing we are going to do is actually strain controlled because we got gearbox essentially and gears change the rate of loading. Okay, rate of loading has got something to do with the permeability of the soil, which is going to be testing on sand or clay. So it's always a strain control testing, essentially. Okay, but we know by common sense that if you are going to conduct test at very fast rate, not considering the pore pressure change in that now it's always going to give you higher strength. Any material in the world, actually, the faster you test, the greater is going to be strength. And not necessarily so in soils, but then because in soils, it also depends upon the pore pressure development and its dissipation. So, notwithstanding that now, greater the strain actually which you are considering in the case of soils is always going to depend upon the permeability. In fact, when you conduct axial test, the first part of the test is going to be to find out the rate of consolidation by the stage 1 and decide upon the rate of testing. These students don't do it now, but all research scholars refer to obviously standard books on the subject now, like Bishop and Henkel axial testing, and they decide the speed of the testing based upon the permeability of the sample, which are obtaining in the first phase of the test. First phase is stage 1 of the test actually. So that is going to be there. So we don't have any stress control or strain control systems. That's only in consolidation, some kind of candidates now, 3-dimensional whatever it is now, that is there now. The rest of the questions reference to the code actually, in some of the issues which is raining, I-6403, now there have been also certain amendments to this now. I think you should go through all the amendments now. Have you really gone through all the code completely from beginning to end? Is very important. The second thing is that there are also additions and subtractions over the years actually. When you refer to the latest codes now, actually they are included in that essentially. So I think some of the mistakes you are pointing out are going to be naturally already probably could have been modified because these codes are quite old. So the modifications could have been, corrections have been issued by the Bureau of Indian Standards. That is what I think actually. And so the mistakes is pointing out in point 9 and 10 actually refer to this now. The last thing I think I want to address is good doubt. I mentioned clearly that when you do direct shear test for a sand, we will get 1.5, let us say. When you do the triaxial test on sand, we are likely to get a different value. Now, which value is going to be more now? I address this also. In a triaxial test, the confining pressure is going to be there. That means, in the both x and y directions, sigma 2 is equal to sigma 3 equal to confining pressure or the cell pressure. In the case of a direct shear test, is not so because it's confined. So that test of direct shear represents a plane strain condition. And obviously, plane strain condition is one in a continuous footing. In other footings, it's not necessarily so. So most people don't really bother about it. They simply say phi. But correctly speaking, direct shear test value should refer to in a continuous footing, and the normal phi value can be triaxial phi value can be referred in other things. Now the difference between these two things is actually found to be 10% now. For example, when I am trying to design a foundation for a geosynthetic reinforced soil wall, actually, what I do, I recommend that it should be done by direct shear, or if I do my triaxial now, it's going to be 10% more actually the phi value. So this is also very important for us to understand actually. The phi value depends upon the confining conditions and also how much movement is going to occur actually. How much movement of the soil is going to occur realistically in the field. And that is related to, because unless a certain movement occurs actually, unless certain deformation occurs, the peak strength is not mobilized. And if the movement is going to much more, I already mentioned that it could become a critical void ratio. That means the strength is going to be not peak strength, it's going to be naturally residual strength actually. So that is a matter of pure solid mechanics. I don't expect the structural engineer to understand and to appreciate the essence of all of them now. But I would suggest that you go to iGrip site of the IIT Gandhinagar, I small and G capital, iGrip. So this is part of IIT Gandhinagar's website actually. And in that probably you will find the videos or at least the PPTs of a short course we have done essentially for foundations for structural engineers, wherein some of these concepts have been enunciated very clearly. Otherwise, of course, you can contact Professor Amit Prashant or Professor Ajinta Sajan to get more details on this now, because that was addressed towards the structural engineering solely. Actually, this entire course is called FDP. It is a faculty-driven program. We are, of course, invited, the field is also, but it is for those who are in the teaching profession. We are trying to say that, okay, you have to do this and this and this, appreciate the concepts involved in this, and then also follow them up in teaching and in doing your assignments, or of course the mini projects. They keep doing it now to give the fundamentals. And I have repeated a number of times that the substitution of these values in equations is just the beginning. We don't need BTech or BE for doing this work. Even any graduate, any school final student can do this, fitting this graduation to this now. There's much more actually to understand to actually complete design a foundation for multi-source structures, whether it be in Hyderabad and Rocky Strata, or in offshore or onshore and near shore, and in black on soil or in silty soil is an art actually. So that is what we have to understand. So I try to focus on issues related to these things actually. Okay, more than actual calculation, because calculation can find in this. The last thing that I address you very clearly is that somehow the tendency of all the teachers essentially, may not be all teachers, quite a few teachers, is to follow simplified solid mechanics books. That means, wherein equations are given and some substitutions there and some problems are solved. They are only textbooks. It will not be useful for practice. For practice, you have to refer to actual codes now. The codes are quoted in the so-called textbooks, or their books are following for teaching. They are only just quoting. They are not giving you totality of what does the code really say, what conditions are going to use it, and things are not really specified in the books. To understand more, I also mentioned that you have to really read the classical books to understand the behavior, because soil behavior can't be controlled by any equation. There's much more to be gained in this now. And the reason for this is actually shown in the country by by lakhs of crores actually, which are spending on projects which have got both time overrun and cost overrun and unfinished projects now. And naturally, all of us are concerned that projects are not complete because of the so-called geological surprises. Geology, I mentioned, is also geotechnical, because in the government's nomenclature, geotechnical is included in the geological portion. That is what I showed in the first slide actually. So unless we are able to put focus on this now, the total system actually which are having, we will not be a successful geotechnical engineer. Thank you very much, sir. Over to you,
Sir.
Professor Reddy Garu.
Thank you very much, sir, for a very detailed and informative lecture on settlement analysis of foundations. You have explained not only the theoretical methods of estimating settlement of footings using the soil parameters determined from laboratory tests, and also by using field tests. You have explained how to arrive at settlements and all. And importantly, you have pointed out that for field practice, just mere reading of textbooks is not sufficient, because in textbooks they only quote some of the codal coefficients. For thorough understanding, one should go through the code in total. So that will really make them well conversant what they have to do and all. And not only that, reading a single book also does not give a complete picture. One should read standard books on foundation engineering. Right? Of course, we have Bible right in foundation analysis and design written by Bowles, and we have some foundation design manual by N.V. Naik. So many such books are there. So one has to refer to such books. In addition to whatever books generally they refer, like Arora, Gopal Ranjan. So additional reading is required. So that is what Sir was mentioning. And I hope all of you might have gained a lot of information from his lecture, which is based on his vast teaching, research and consulting experience. Very rarely we will get such an opportunity to listen to a lecture of that standard. So in case if you have any doubts regarding the presentation made by Professor G.V. Rao sir, you can interact with him.
Sir,
His email ID is also posted with the SAR's permission. Maybe if you have a valid discussion, maybe you can contact SAR later also.
Yes, sir. Sir, I have some question. Can I ask?
Yeah, before Karthikeyan asks a question, I would like to make a small announcement. Since today's afternoon scheduled lecture was completed by Dr. Neelima on the first day because of her some other commitments, right? So today evening session I will be engaging. I will be covering the topic of combined footings. We will discuss about types, right, under what situation they will be used and how to proportion them. Okay, so be on time at 4 o'clock. Now we'll proceed. Sir, can we take some more questions from the participants, sir?
Yeah, maybe 5 minutes because I have a meeting at 11 o'clock.
Yeah, that's what, sir. IRC H4 committee meeting is there.
Yeah.
Maybe.
No, whatever we can take up now, the others can be channeled to me. For 30th we can keep it.
Okay, sir.
One or two I can take up now. Let us see.
Okay, Karthikeyan, you can pose your question.
Yes, sir. Thank you, sir. Sir, regarding the samplings, so let us say on site, sometimes we cannot recover some undisturbed samples. So
Yeah.
if we collect the disturbed samples, then if we do the conservation test in the remolded samples, how much the result variation will come from the undisturbed and the remolded samples, sir?
No, that depends on sensitivity of the soil. It's not something which you can say so easily. It's not something which you can say so easily because that depends on the type of soil itself actually, and the degree of disturbance which you are going to cause, why it has been caused and things like this. Isn't it? You see, one thing is there. Any undisturbed sample will be definitely, we can say, will be having much lower strength, is it not, than the original sample. I mean, any disturbed sample is going to have much lower strength than the natural soil, is it not? Disturbance is going to be disturbed really. Disturbance means really disturbed, the structure is disturbed, the biodiversity is disturbed now, and how big the sample is. Supposing the sample is quite big now, suppose assume that it is 75 millimeter diameter. Okay, maybe the central portion is less disturbed now. In fact, that's what I told you, the subject of investigation is so great detail, we just gave you overview of that now. You have to go through to understand more disturbance. The book by, I told you, Howard Slave, I gave a presentation, I gave a the title also. Subsurface investigation sampling by Herslev, which is a very classical book on subject, and also there are many other books also. So it is very difficult to pinpoint or say that there is 10% disturbance something. The entire thing is changing. Now, how do you get a pre-construction pressure actually in a disturbed sample, isn't it?
Yes, that's right.
So it is not getting back the same void ratio, initial void ratio. It is actually total structure in the disturbed. Structure means everything disturbed. It could be having say salty water, something that now. It can have bonds actually, weak bonds which are there now. That's why a natural soil will be definitely having a much different characteristics compared to the disturbed soil.
Okay, sir. But in that case, how much we can rely on those numbers? Can we say that we
We can't
cannot rely on completely?
We can't rely, obviously. That is very, very clear. We can't rely on that now. To get a best sample, actually, there are methods of sampling. There are these
Like
standards
drop
and different. We give you that also. In fact, the different IS codes also give you all the details actually. But one thing is people are not following that. See, even the sampler they're having is a very rough and crude, and it's not oiled also, neither inside nor outside, and the screw it doesn't fit tightly, and the check valve is not at the top now. So many things which can be done also not being done now. That's what I'm saying. So first take care of that now. How not instead of inquiring if you disturb what I'm going to do, why not you try to get the best standard sample, which is quite easy, provided you're sincere on that, provided the authority is sincere. That's what we are trying to say, that it's not left to the driller, the boring fellow, the fellow who does boring in houses for water actually. That fellow is being engaged to get sampling. That fellow is being engaged to SPD. He has no clue on what is happening. It's not supervised. He just gives some data, and then he throws on your face some sampler actually, some sample tube. So there are things which we can do ourselves actually to more carefully, first by going to the site, first by ensuring that your spiritual sample is correct now, it has got the same standard, it's got the check valve at the top now, it's oiled at the top now, bottom is conical properly, shampooed appropriately, not broken down actually, and your sampler also, if not shall be tube, the tubes you are having will be very rough, very crude, they never oiled it also, it doesn't fit in the top now, it doesn't have again check valve at the top now. So many things can be done actually by this now. Isn't it? First of all, we should ensure that the best sample obtained within circumstances. Then, for a major project now, there are many methods of sample retention, many methods of obtaining it now. As I said, we are not teaching all that now, but there are many methods which are in textbooks also given the code also, and then we refer to classical books. And for offshore, I'm not doing it actually. Offshore work we're doing like that only better now. Isn't it? So it is a subject by itself which can be easily practiced to some extent within our limits also. Supposing conduct an SPD, how many people have gone to the site to see the SPD done actually? Do you think that it's going to drop in the same way vertically? Is it got friction at the sides now? Is the weight at the same thing now? The number of blows at the same rate as specified actually? Is it too fast? Is it too slow? Is what table being maintained on? I can give you a list actually. This list of errors which can go wrong is given in the US Army Corps of Engineers book into 4 pages. There are 100 mistakes which you can do in this one. So the thing is that I think maybe our Professor Reddy will conduct another course, or one of you should take initiative and understand the issues which are concerned, which can be practiced also. In fact, that is a big issue all of us face in the country. The lack of proper investigation is the main thing now. Agencies also, because they are forced to quote only based upon quotation only. And actually, whoever says there are good companies now, but they are not in business really because they quote high. Somebody quotes, let us say, even good government agencies are quoting. You'll be surprised to know. I can show you some sites wherein they say that liquid limit is going to be 40 rupees and master guarantee is 50 rupees. Well, how can it be? So these rates which are getting actually for tendering are above low actually. Or track shelter they will say 25 rupees. How can 25 rupees track shelter you can do? So the point is that now with all these L1 business now we are out of the picture. So anyway, issues are different now. So my appeal to anybody is that first try to be as sincere as you can within the limits to be. First, that itself doing 50%, let's say, undisturbance. Okay. Thank you. Then I think we discuss on 30th again.
Thank you, sir. Thank you, sir.
Let me have some coffee tea before I have the next meeting.
Yeah, thank you very much, sir. for patiently answering to the queries of the participants.
No, we are here for that only. Isn't it?
Because you have another hectic session now with ERC, the H4 committee meeting. So
Yeah,
thank
yeah,
you.
we have the meeting after that also. In the afternoon, we have the BAS meeting. So,
Oh,
yeah, that starts from 4:30 to 8 o'clock or something. Like that.
sir.
Today is a busy day, actually. Anyway, we are here to.
Thank
No.
you very much, sir, for sparing your valuable time. I thank all the participants for your active participation in the morning session. We will meet again in the evening at 4 o'clock for lecture on combined footings. So try to join on time so that we can finish right before 5:30. So thank you all.
Thank you. See you and namaskar.
Thank you all. Have a good day. So before leaving, try to submit the attendance for the morning session using the Google link which is shared in the chat box. So if any of you need attendance links of yesterday, for some reason you could not submit, you can contact Mr. Vishwateja. We will provide you with the link. After verifying for your presence, right? Okay, then we'll meet in the evening. Thank you all once again.